Welcome back to my YouTube channel. In this video, we will take a look at diagonalization and how to find a solution to dynamical systems. Please like, share, and subscribe to my YouTube channel. For every dynamical system, it is important to know that there are some few steps to take to solve them. We will write down the steps that we are supposed to take to solve these questions. We have 1, equilibrium point. Your equilibrium point. The second thing you have to find are your eigenvalues. Then you find your diagonal matrix. And then your diagonal matrix is given by D. Fourth, you have to find your eigenvectors. Our fifth step is to find our matrix of eigenvectors. And the sixth one to find are your exponent of diagonal matrix. Or should I say the exponential? Exponential of diagonal matrix. So these are the 6 steps that you're supposed to take and find or solve for the solution of the system. Our equilibrium points, which are given by, these are vectors, which belong to n. Your eigenvalues, lambda I, so different eigenvalues. Your diagonal matrix D, your eigenvectors Vi, your matrix of eigenvalues, which is P, and your exponential of diagonal matrix D. So if you have all these things available, you can go ahead and solve for the solution of your system. Now remember, you are mostly given an initial condition, which is x naught given by, it can also be written in this form. Every linear system is given by x dot equals ax. You are given an initial value problem since you have your x naught. For the first step, since we are dealing with a linear homogeneous case, the equilibrium points are always at the origin. So for linear homogeneous systems, the equilibrium point is always at the origin. So for linear homogeneous systems, the equilibrium point is always at the origin. The second step is to find our eigenvalues. Our eigenvalues can be gotten by diagonalizing the matrix. And there is a theorem that supports that. So for diagonalization, if we have the eigenvalues lambda 1, lambda 2, up to lambda n, which we get from an n by n matrix A, so A is n by n, and we have the eigenvalues to be real and distinct. So real and distinct, which means our lambda 1 is not equal to our lambda 2. We have different values. So we can have lambda 1 to be 2, lambda 2 can be minus 2. They are distinct. Is that okay? One is positive, one is negative. Or we can have both of them to be positive. So we can have lambda 1 to be equal to 2 and lambda 2 to be equal to 3, lambda 3 to be equal to 4, lambda 4 to be equal to 1, and so on and so forth. Since this is an n by n case, our eigenvalues are actually up to the nth value. So we have lambda n to be equal to whatever number it is. So the eigenvalues have to be real and distinct. And we also need to find a set of corresponding eigenvectors. Like I said, for every eigenvalue, there is a corresponding eigenvector. So this set of corresponding eigenvectors will be from V1 to Vn. Now I said the set, so you see I'm using a curly bracket. So you find this set of corresponding eigenvectors, and from this set of corresponding eigenvectors, we can find our matrix P, which is made up of all the eigenvectors that you have. And then we can also find our P inverse, which is also a matrix. And we can just write this V1 to Vn, their inverse. Okay, so P inverse is what I've written. Okay, so if we have all this information, then we can write that D, which is our diagonal matrix, is given by P inverse AP. That's going to be our diagonal matrix. And we can write, we said this is given by D. So you can either write it in this form, or you can just write diag of lambda 1 to lambda n is equal to P inverse AP. Okay, so from the theorem of diagonalization, if you're given the linear dynamical system X to be equal to X, initial value problem, X of 0 to be equal to X naught, we have our solution X of t to be equal to the exponential of at X of 0. This is going to be a solution. Now, if we let y is equal to the P inverse of X, it implies that what X is actually equal to Py. It's as simple as that. Now, it also implies that y of 0 is equal to P inverse of X of 0. So now, we want to transform this system. We want to transform this system into a dynamical system. In dynamical systems, we have the phase differential. So we have y dot to be equal to P is just a matrix, which is a constant matrix. So we don't do anything to it. We have x dot Now, we also remember that x dot is given by ax. So we have our y dot to be equal to p inverse ax. Now, we also remember that our x is given by py. So y dot is equal to p inverse a py. Now, we can see that we've transformed this expression into a dynamical system, which we have here. Now, this system that we have, the first system, which is a linear system we have here, is a coupled linear system. It implies that we have both x and y variables in it. This system we will have here will be uncoupled. There is only one variable, meaning there is only one variable for each vector. So if we have y1 and y2, their first differential, let's say ay1 and by2. This expression has only one variable, whilst the first expression x1 dot x2 dot could have a x1 plus b x2, and this one could have c x1 plus d x2. So this is the coupled system, meaning it has both x1 and x2 variables in the expression. All this is an uncoupled system because it has only y1 in the first equation and only y2 in the second equation. Now, if we want to find the solution to this dynamical system that we have created, it's going to be y of t equals now, if we recall, the first expression that we have here has a solution. So this x dot equals ax has a solution, x of t equals a of t x naught. So you see that we took the exponential of the value, the matrix A. So you're going to do the same thing to this. This is a matrix. We recall that our diagonal matrix is equal to P inverse AP. So we make a substitution. We will have as our substitution y dot to be equal to the diagonal of all the lambdas, lambda 1 to lambda n, lambda 1 to lambda n, multiplied by our y. To find the solution to this dynamical system that we have here, we find the exponential of the system. So we have e raised to the power the diagonal of the elements here, lambda 1, lambda n, multiplied by y of 0. So we have y of t, we have y naught. We substitute this value into the expression x is equal to py. Now remember, this x is the same as x of t, and y is the same as y of t. So we have p, y is given by this expression. We have e raised to the power the diagonal of lambda 1 up to lambda n multiplied by t, and we have y naught, which is given by P inverse x naught. So we'll have P inverse x naught, which is the same as x of 0. So this is going to be a solution. We can also rewrite this solution as P e of t, P inverse x of 0, where e of t is given by the diagonal e raised to the power lambda 1 of t, e raised to the power lambda m of t. Is that okay? This expression is the same as this expression. Do not worry, it's the same thing. So we've taken a look at these processes, and then we find our eigenvectors, and we find our exponential of the diagonal matrix E of t. These are the processes that we will use to find any of the solution of our dynamical system. The first step is unnecessary because the equilibrium points are always at the origin for the linear homogeneous systems. But for other systems, linear non-homogeneous systems, you have to find the equilibrium point. We will take a look at that in the future. The next one, you have to find your eigenvalues. So these are the first steps that you must take. Find your eigenvalues. So we'll label that as 1 here for linear homogeneous systems. Then you find your diagonal matrix. That will be our 2. You need to find your eigenvectors. That will be 3. You need to find your matrix of eigenvectors, which is 4. And you need to find the exponential of your matrix, which is 5. These 6 steps has been reduced to 5 for linear homogeneous systems. We will take a look at an example right away. If our matrix is given by 0, minus 2, minus 1, minus 3, the first thing we're supposed to do is find our eigenvalues. And how we find that is using the determinant and trace approach. So for all 2x2 systems, just use this approach because it's easier and faster. The first step is to find our tau, which is our trace, and our determinant. We add the trace of our system, which is the diagonal. We have 0 plus minus 3, which will give us minus 3. For our determinant, we'll have 0 times minus 3 minus 1 times minus 2. So we have 0 minus 2. And this will give us minus 2, which is less than 0. And we can conclude here that since the determinant delta is less than 0, the system is a saddle at the origin. Now, the behavior of the system is always close to its equilibrium point. That's where we make our conclusions. The equilibrium point of every linear homogeneous system is at the origin. That's why we are concluding that the system is a saddle at the origin. We can go ahead and find our eigenvalues, which is given by this expression, tau plus or minus the square root of tau squared minus 4 delta divided by 2. So with this, we insert the value of tau and delta. So our lambda is equal to minus 3 plus or minus the square root of minus 3 squared, give us 9, minus 4 delta. So this is going to give us 4 times minus 2, 4 divided by 2. This is going to be equal to minus 3 over 2 plus or minus the square root of 9 plus 8, give us 17 over 2. So our lambda is going to be equal to minus 3 over 2 plus or minus the square root of 17 over 2. Lambda 1, take your first value to be negative. So we have minus 3 over 2 minus square root of 17 over 2. And lambda 2 will be minus 3 over 2 plus the square root of 17 over 2. Now remember, the square root of 16 is 4, and 4 divided by 2 is 2. We'll have 2 here, approximately 2 point something. So 2 here. And minus 3 over 2 is minus 1.5 or minus 1.5. So we can see clearly that this is greater than 0. So we have lambda 1 to be less than 0, lambda 2 to be greater than 0. And this is clearly a saddle, like the conclusion we had above. So we've confirmed the behavior of the system. Since we have our eigenvalues, we will go and look for our eigenvectors. Our lambda 1 was minus 3 over 2 minus the square root of 17 over 2. And our lambda 2 was minus 3 over 2 plus square root of 17 over 2. So we know the expression for finding our eigenvectors. A minus lambda I multiplied by the vector is equal to the 0 vector. So for our first eigenvalue, we'll have A minus 3 over 2 minus the square root of 17 over 2 times V1 is equal to 0. And this is multiplied by our I. We can factorize the negative inside to have A plus 3 over 2 plus the square root of 17 over 2 times I multiplied by our V1 is equal to a 0 vector. So we substitute the value of A. A was given by 0. You can look at the value of A. You have 0 minus 2, minus 1, and minus 3. So we have 0 minus 2 minus 1. So we have this plus 3 over 2 plus square root of 17 over 2 times the identity. And all this multiplied by V1, which is equal to 0. This is going to be 3 over 2 plus square root of 17 over 2 minus 2 minus 1. We have minus 3 plus 3 over 2 plus square root of 17 over 2 multiplied by your vector is given by x and y to the components of the vector and 0, 0. Always use the first line to multiply your vector that you have here. That's all we need. So we have 3 over 2 plus square root of 17 over 2, which are multiplying your x plus minus 2 multiplying your y is equal to 0. The first equation is all you need. We'll have 3 over 2 plus square root of 17 over 2 is equal to 2y. Sorry, multiplied by x. If we multiply both sides by 2, we're going to have 3 plus the square root of 17x is equal to 4y. Remember, we're going to divide y over x. So the expression you're going to have, it will be 3 plus square root of 17 divided by 4. We will state our hypothesis and then we'll state our thesis. So if y is equal to 3 plus the square root of 17, then, so this is your hypothesis, then x will be equal to 4. So if this, then that. So this is the first expression. So our v1 will be equal to x is 4, for y is 3 plus square root of 17. Our lambda 2 to be equal to minus 3 over 2 plus the square root of 17 over 2. We have a plus 3 over 2 minus square root of 17 over 2 times I multiplied by v2, giving us our 0 vector. A was given by 0, minus 2, minus 1, minus 3, plus 3 over 2 minus the square root of 17 over 2 multiplied by I, v2. So now writing this down, we'll have 3 over 2 minus the square root of 17 over 2. You have minus 2 here, minus 1, then minus 3 plus 3 over 2 minus the square root of 17 over 2 multiplied by our v2, which is given by x and y. So we just need our first expression. So the first value multiplied by this value. So we'll have 3 over 2 minus square root of 17 over 2 multiplied by x minus 2y is equal to 0. Then we're going to have 3 over 2 minus the square root of 17 over 2 multiplied by x is equal to 2y. Multiplying both sides by 2, we'll have 3 minus the square root of 17 multiplying x give us 4y. So again, our y divided by x is going to be 3 minus square root of 17 over 4. So if y is equal to 3 minus the square root of 17, then, so our hypothesis, then our thesis will be, then x will be equal to 4. So for our v2, we will have x to be equal to 4, y to be equal to this. So our P matrix is given by V1. It's in the form of a matrix, not a set. V1, V2, the matrix form. So our P is going to be 4, 3 plus square root of 17, and 4, 3 minus square root of 17. If we want to find our P inverse, we have to find the determinant of P. So the determinant of P is given by 4 times 3 minus square root of 17 minus 4 times 3 plus the square root of 17. This is going to be 12 minus 4 times root 17 minus 12 minus 4 square root of 17. So we're going to have, answers this, we're going to have minus 8 square root of 17. P inverse is given by 1 over the determinant of P multiplied by the adjoint 3 minus square root of 17, 4, then minus 3 minus square root of 17, and minus 4. So 1 over minus 8 root 17 square root of 17 over minus square root of 17 over 8 times 17, which is 136. So it is going to give us minus square root of 17 over 136. We rationalize the denominator, that's why. So our P inverse is going to give us minus square root of 17 over 136 multiplied by this value, 3 minus square root of 17. We have minus 4 minus 3 minus square root of 17, 4. So we have our P inverse. We need to find D, which is the diagonal matrix. Now remember, your D is just made up of your eigenvalues. How you found your eigenvectors is how you are going to arrange your eigenvalue. So we use the negative eigenvector first. So you're going to have minus 3 over 2 minus square root of 17 over 2, 0, 0. And you're going to have minus 3 over 2 plus the square root of 17 over 2. This is going to be your diagonal matrix, which is the same as P inverse AP. You can confirm that, you can multiply that and check. Your exponential of the diagonal of your lambdas, so lambda 1, lambda 2, multiplied by t. So this will be, you're going to have e raised to the power minus 3 over 2 minus the square root of 17 over 2, all multiplied by t, since we have t here. Then 0, 0, e raised to the power minus 3 over 2 plus square root of 17 over 2, all multiplied by t. So now we have all the information. This is also given by e of t. So we have all the information now. So the solution of our system, which is given by P E of t, P inverse x of 0. Now this can sometimes be given. You just do matrix multiplication to find your solution. So since we have all these ingredients, we just substitute them and you can find the solution of the system. In the next video, we will take a look at other examples, including 3x3 systems and how to solve for the characteristic equation, as well as finding the eigenvalues and finding the solution to the system. Thank you and see you in the next video.